In this lecture, we will discuss about the parallel AC circuits. The objective of this particular lecture is to cover RL parallel AC circuit, RC parallel AC circuit, and RLC parallel AC circuits. So the parallel AC circuits are those AC circuits in which the circuit elements are connected in parallel to one another across an AC source. So let us start with the first, which is parallel RL AC circuits. So before that, as I mentioned, that any parallel AC circuit is the one in which we have an AC source and we have the various circuit elements which are connected to one another in parallel to this particular AC source. So in this way, we have many circuit elements which are connected to this AC source, which is V is equal to Vm sine theta. So now, as you can see, if let us say capital V is the RMS voltage and capital I is the RMS current, so this current will divide into all the branches here. So let us say this is I1, this is let us say I2, and this is, for example, IN. Now, so this is a parallel circuit basically, or you can say this is parallel AC circuit. Now, why it is a parallel AC circuit? Because these all elements are connected to this particular AC source, right? Now, there are certain features of the parallel circuits. For example, the current in any branch of this particular network is that depends upon the impedance of that branch. So let us say this block is basically the impedance of this particular branch, and this is the impedance of this particular branch, and this is the impedance of nth branch of the network. So we can say that I1 is equal to V by Z1, I2 is equal to V by Z2, and so on. We have IN is equal to V by Zn. So that means the current in any branch of the network depends upon the impedance of that particular branch. And also, this is the first thing. The second thing is that the total current is basically the phasor sum of all the currents that are present in the, or that are divided into the branches. So we will apply KCL at this particular junction, right? So we have the total current which is equal to the sum of all the branch currents. Most of our electrical systems, they use parallel connections, right? Then series. Now, why? Because as we can see that, let us consider a bulb, a fan, and a TV. So the power voltage rating of all these is same. That is 220 volt to 240 volt AC. But they have different current ratings. So we prefer to connect them in parallel to the AC source. So let us say that a bulb will be connected first of all, and the fan will be connected. So fan is an RL load basically. So it will be connected like this. And then we have a TV basically. So TV will be connected. So bulb is there, fan is there, TV is there. So the purpose of connecting them in parallel, now why they are connected in parallel? Because they all have to share same voltage, because their voltage rating is same, right? So they will be sharing the same voltage. So we have used a 220 volt to 240 volt AC source here, right? And they are sharing the same voltage. Every component have the same voltage. So that is why we connect the electrical appliances in parallel. Even in our home also, all our electrical appliances are connected in parallel to the input supply, the AC supply. And the reason is same, because all the electrical appliances have the same voltage rating. They have to be provided with the same voltage, but their current ratings are different. So as we all know that current divides in parallel connection. So every element will share the part of current according to its impedance, right? So now this is what a parallel system is. Now we have the various types of parallel connections. We have parallel uh, RL connections, we have parallel RC, and then we have parallel RLC. As you can make out from the names here, that in this we have R and L are in parallel to each other. Here we have R and C are in parallel to each other, and here we have R, L and C are in parallel to each other, and all these are connected across an AC source, right? So first of all, we will understand about the parallel RL circuit. So let us discuss the parallel RL circuit first. So a parallel RL circuit or parallel RL AC circuit is the one in which we have an AC source, we have a resistance, and then we have an inductor connected to one another in parallel to this AC source. So this is V is equal to Vm sine theta, and we have the RMS values of voltage and current, and then this is the resistance, this is the uh, inductance basically, and we know that XL is the inductive reactance, which is equal to 2 pi FL ohms, and this F is the input frequency, right? So let us say the current in this branch is IR and the current in this branch is IL, right? So this is a parallel RL circuit. Now V and I, these are the RMS values of V and I respectively. Now what is V and I? These are the instantaneous voltage and current respectively. So V is equal to Vm sine theta. Now what about I here? Now because this circuit is an inductive circuit, so the current will lag the current will lag the voltage by some angle phi, right? So it is I is equal to Im sine theta minus phi. So these are the instantaneous values of voltage and current, right? Now, so let us understand its analysis. Uh, the current basically here. So let us come to the analytical part here. So let us divide this screen. So we will understand its analysis now. So the first thing that you need to find out is the current. So current is equal to IR plus IL, because the voltage at this point is V and the voltage at across this element is also V. Why? Because they are connected in parallel, right? Now, so I is basically, it is the total current, and IR and IL are the RMS currents through R and L respectively. So I is given by, because it is total current, so it is V by Z. IR is equal to V by R, and IL is equal to V by JXL. Now this Z is the impedance, right? This is the impedance. So if we substitute all these values into this equation, we get V by Z is equal to V by R plus V by JXL. The first thing that we understood is that how to find out the current. So the total current can be obtained by adding the currents in each branch. It is a phasor sum of the currents in each branch. Now, now if we substitute the values here, equations here in this equation, so this is for example equation number 1, and here taking V common here, so we have V by Z is equal to V 1 by R plus 1 by JXL. So V and V is cancelled out. So we have 1 by Z is equal to 1 by R plus 1 by JXL. So this is, for example, our equation number 2. Now, in parallel AC circuits, basically, we generally prefer to use the we prefer to use admittance instead of impedance, because using admittance instead of impedance in parallel AC circuits has its own benefits, its own advantages. Now let us go further. Admittance is basically nothing but it is denoted by Y, and it is equal to 1 upon impedance. So it is the reciprocal of impedance basically, right? So it is measured in Siemens or mho. So this mho is the reciprocal of ohm, right? So similarly, so 1 by Z is equal to Y, which is admittance, and similarly 1 by R is G, which is the conductance, and its unit is also the same, S or mho. And similarly 1 by XL is equal to BL, which is known as inductive susceptance, and again the same units, Siemens or mho. So if we substitute this all in this equation number 2, so we get Y is equal to G plus BL by J. Now this J can be factorized here, so we will multiply it here J by J. So we will get G plus JBL by J square. So it is G minus JBL, because J square is minus 1. So Y is equal to G minus JBL, right? So like as you can see here, using admittance is more convenient or comfortable to use, right? So here if you see, we have to take the parallel combination of the impedances, right? So this is a bit complicated. Now here it is a bit easy. So we can find out the conductance of the circuit, we can find out the susceptance of the branch, and then we can add them algebraically, right? So it is quite easy for us to analyze the things in terms of admittance, conductance, and susceptance. So now let us come to the circuit diagram basically, which we can draw in terms of the Y and BL. So the circuit diagram can also be drawn in terms of B and or BL and G. So we'll take the same circuit diagram as drawn here. So instead of using R and XL, we will use B and G. So the things will remain same as it is. Nothing will change. Only the way we denote the circuit components will change. So RMS value of applied voltage is V, capital V. RMS value of input current is capital I. This is an AC source. And instead of writing R here, we will write G. So G is basically the conductance, and the current here is, let us say, IG, and current here is, let us say, IBL, for example. So instead of writing this as XL, we will write it as minus BL, right? So this is how we can represent the given circuit diagram of parallel RL circuit in terms of the conductance and the susceptance. Now let us come to the phasor diagram. So let us understand the phasor diagram. So as you can see here, this current IG and this voltage, because this component has the same voltage V, and this component also has the same voltage V. So in conductance G, IG and V are in phase. So G is the in phase component of Y. Now in susceptance BL. Now here, as you can see, the voltage and current, they will have a phase difference of 90 degree. Now because in this circuit, parallel circuit, voltage is the common component, so we will take voltage as the reference phasor, and then we will have this IBL, for example, right? This is how we can have, or IBL or IL. This is just a notation, so we don't have to confuse with the notations here. So and in this G we have V and then IG, both are in same phase. So in susceptance BL, IG or not IG, basically IBL lags V by 90 degree. So BL is the quadrature component of Y. Quadrature component means the component which is at quadratic, basically forming the quadratic formation. Like you can see, it is a quadratic formation. 90 degree is lagging from V, so it is a quadratic formation. So now let us draw the phasor diagram here. So we have like here in this conductance, we have V and IG, both are in same phase. Here we have V and IBL, 90 degree phase difference. So voltage V is the common component across each circuit element. So hence voltage V is taken as the reference phasor. Now, so let us draw the voltage, or let us draw the current first of all. Now the current is, this is IG or IR, one and same thing, right? So then we have the voltage phasor. This is V. Now IG or IR are in phase with V, and then we have the um, you know the IBL or IL component. So we will draw it again. So this is your IL or IBL, right? So now this is lagging 90° from the voltage. This is the voltage phasor, and your current in the inductor is lagging the voltage by 90 degrees. So the resultant phasor is this one. Now this is what we say, that this is the resultant current, which is I, and the phase angle, phase difference is phi. Because the circuit is inductive, so you can see that the net current is lagging the voltage by 5 degrees, right? So you can see the same thing is coming out here. So we can draw this in a simple current triangle, and the current triangle would be this one. So we will take it as IR, or we can take as IG also, doesn't matter. So then we have IL, and then we have the I, and the phase difference is phi. So this is basically a right angle triangle, which we call as the current triangle. Now in this current triangle, if you see, this I is basically the phasor sum of, okay, so we'll write here from the current triangle, we can observe that I, which is the total current, is the phasor sum of IR or IG and IL or IBL, right? So now if you divide this particular parameter with V everywhere, because V is the common component, right? So now if this is done, I by V is basically nothing but I by V is nothing but it is 1 by Z, which is equal to admittance Y. And similarly, IR by V is nothing but it is 1 by R, which is equal to G. And similarly, we have IL by V, which is equal to 1 by XL. So it is equal to, or JXL basically. So it is equal to minus BL. So I'll make it a little bit clear. So this is a little bit messed up here. So no, I'll write it here, right? Sorry. So this is IL by V is 1 by JXL. So it is minus BL. So we have this part, and this part. So if we divide the each phasor of this current triangle with V, so we will get a new triangle, which we call as the admittance triangle. So I by V, this is G. Then you have minus BL, and then you have Y. Fine. So this is known as admittance triangle. So from here, the given equation is justified, which says that Y is equal to G minus J BL, right? So now, as you can see, Y is equal to G minus J BL. So the magnitude of Y is, so the magnitude of any complex number is always the square root and the square of real part plus the square of the imaginary part. And the phase, basically this phase, if you want to calculate the phase here, so the phase angle of phi is given by, it is given by phi is equal to tan inverse the imaginary part divided by real part. So this is what your phase angle is. You can make out from the impedance triangle here. Okay, if you see the impedance or admittance triangle, right? So admittance triangle is G, then you have minus BL, and then you have Y, right? So this is phi, right? So because this is negative, so the value of phi will always be a negative value. Negative value means it will be in the quadrant where tan is negative, right? So BL, perpendicular by base is tangent theta. So this is how we have got this one. So in a parallel RC circuit, if we have to compute this one, so in a parallel RLC circuit, or so parallel RL circuit, we have the current is basically given by IR plus IL, the phasor sum, or IG plus IBL, and the total admittance. This is the total current. This is the admittance. It is given by G minus JBL, right? And the magnitude of Y is given by under root G square plus BL square, and the phase difference is given by tan inverse BL upon G. So now this is about the RL. Let's come to the parallel RC AC circuit. Now, as the name suggests, a parallel RC AC circuit is the one in which there is a voltage source which is AC in nature, and two components which are a resistance and the capacitor are connected to one another in parallel across this voltage source. V is equal to Vm sine theta. So this is an AC source here. So let capital V is the RMS value of the voltage and capital I is the RMS value of the input current. So each branch will have some current which is IR, and let us say it is IC, for example. So V and I are the RMS values of V and I. Now, because this is a capacitive circuit, right? So in a capacitive circuit, the current I leads the voltage V by an angle phi, right? So if V is equal to Vm sine theta, then I is equal to Im sine theta plus phi. So these two are the instantaneous quantities of the source, right? Now, so these are the two quantities, fine. So let us see this total current, the I, capital I, which is, now let us come to the analysis of this one. So this is it. So the analysis part says we have to find out the total current. So first of all, we will see the total current. So the total current I is basically equal to IR plus IC. Now, I is equal to V by Z, and Z is the impedance. So this is the impedance, right? IR is equal to V by R, because these are the parallel circuits, parallel components. So this is sharing V here. This is also sharing capital V here, right? So this is impedance. And now similarly, we have IC. So IC is equal to V. Now it is JV by XC. Now the reason why we take JV by XC, because we know that XC is equal to 1 upon J omega C, right? So if we put this here, so IC is equal to V by 1 upon J omega C. So 1 upon omega c is the magnitude of the xc. So j will come here. So it would be this one. So if we substitute all these values here in this one, so we get v by z is equal to v by r plus jv by xc. So we will take the voltage common because it is the common component here. So we will take this as common. So let us remove these things from here. Now, so we have v by z is equal to, taking v common in this part, we have 1 by r plus j 1 by xc. So now v is cancelled out here. So we have 1 by j is equal 1 by z is equal to 1 by r plus j 1 by xc. So 1 by z is the admittance, 1 by r is the conductance plus j, and this is the susceptance, the capacitive susceptance. So BC is the capacitive susceptance. And the unit of this is also the same as that of Y and G. Now, the given diagram can also be drawn in terms of the G and BC. So we have this one with us. This is a voltage source, then we have the resistance, and then we have the capacitance with us. So this is V. Capital V is the RMS value of the voltage. Capital I is the RMS value of input current. Instead of writing it as R, we will write it as G and this as BC, right? So the current here will divide, let us say this is IG and this is IBC. So now this was about the admittance and total current. So the magnitude of Y is, so the magnitude of Y is basically the square root and then square of the real part and the square of the imaginary part, right? Now, so now let us come to the phasor diagram here. So in phasor diagram, so phasor diagram of a parallel RC circuit. V will be the reference phasor, right? And we know that in a resistance or the conductance, the current, which is IR or IG, are in series or in same phase with the voltage, right? In phase, both are in phase, this and this. Similarly, in what you call as the susceptance, the capacitive susceptance or capacitance. So in a capacitor or susceptance, which is capacitive in nature, so the current, which is I, what do you call as IC and or basically IBC, it leads the voltage by 90 degree. So we'll write here IBC or IC leads V by 90 degree. So by taking these two in consideration, we will draw the phasor diagram of parallel RC circuit, and the phasor diagram would be like this. So first of all, we have the current phasor IR or IG. Then we have the voltage phasor because voltage is the common component. So this is V. Then we have the the current basically, which is leading the voltage by 90 degree, and that current is IC or IBC. So this is IC or IBC, right? So it is leading the voltage by 90 degrees, right? So the resultant current will be the phasor sum of these two currents, right? And the angle, this is I, total current, right? So this is the phasor diagram of the parallel RC circuit, right? So this is phasor diagram of the given parallel RC circuit, right? So if you convert this into a triangle, which is the current triangle, so you can do so. So you have IR, then you have IC, or you can write it in terms of G and BC also. Then you have this I, and this is 9. Sorry, this is 5. Sorry, this is 5. This is 90 degrees here. Now you can see this is the current triangle. This is the current triangle. So from the current triangle, you can see that I is phasor sum of IR and IC, right? Which is given here also. This one. So this is the phasor sum basically, right? So this is understood from the given current triangle. Now, if we divide the each, if each phasor of current triangle is divided with V, we get a new triangle which we call as admittance triangle. So let us see. So if we have the current triangle with me, so here I will divide this with Z. This is IC, sorry, not Z, sorry. This is I by V. This is also IC by V. And this is your IR by V. So as we know that I by V is equal to 1 by Z, which is equal to Y. And similarly, your IR by V is equal to 1 by R, which is equal to G. And similarly, we have IC by V, which is equal to J1 by XC, which is equal to JBC. So we will replace this as the same, a new triangle, which is what we call as the admittance triangle. So we have the phase difference here. We have I by V is equal to Y, which is the admittance. Then we have IC by V is equal to BC, which is the capacitive susceptance. And then this is IR by V is equal to G, which is conductance, right? So this is what we call as the this is the admittance triangle, right? Now in this we can obtain that Y is equal to G plus JBC. The magnitude of Y is equal to under root G square plus BC square, and the phase difference phi is, now we can obtain it from here. We have phi is equal to it is phi is equal to tan inverse the imaginary part, which is BC, divided by the real part, which is G. So now this is always be positive. So in this case, phi is positive, right? So this was about the RC circuit, and then we have studied the RL circuit also. We have seen the impedance admittance triangle of RL and then RC, and similarly now we will come to the next, which is RLC. So an RLC circuit or RLC AC circuit is the one in which we have an AC source, and then we have the components R, and then we have L, and then we have C. All elements are connected in parallel to one voltage source, which is AC in nature. So it is V, and the RMS value of voltage is capital V. RMS value of current is capital I. This is the resistance R, inductance L, and capacitance C. So this is IR here, this is IL, and this is IC, right? So no, V and I are the instantaneous quantities, right? So V and I, these are the RMS values of V and I respectively, right? So in this we have one thing which we need to understand, that if your V is equal to Vm sine theta, then I will be equal to Im sine theta plus minus phi. Now why we have taken plus minus? Because the given RLC circuit will behave either as an inductive circuit or capacitive circuit, right? So if it is inductive, then I lags V by angle phi. Hence, I is equal to Im sine theta minus phi. If it is capacitive, then I leads V by phi, that is I is equal to Im sine theta plus phi. So this is how it would act. So we need to understand which of these two components would be dominating. If the inductance is dominating, so the circuit will behave as an inductive circuit. If capacitance is dominating, so the circuit will behave as the capacitive circuit, right? So let us come to the analysis part of this one. So let us come to the analysis. As far as analysis is concerned, so first is we'll try to find out the total current. So it is I is equal to IR plus IL plus IC, right? So now we know that I is equal to V by Z, IR is equal to V by R, IL is equal to V by JXL, or minus V by XL minus J, sorry, right? Okay, so and IC is equal to JV by XC. So if we substitute all these points in this equation number, let us say this is 1, for example, so we have the total current I is equal to V by Z plus, sorry, not V by Z, sorry. So this will be, we'll remove this one. So it would be your V by Z is equal to V by R plus V by JXL plus JV by XC, or V by Z is equal to V is common. So we have 1 by R minus J, 1 by XL plus J, 1 by XC. So V to V is cancelled out here. Hence, we are left with the impedance components. 1 by Z is equal to 1 by R minus J is taken as common. So we have 1 upon XL minus 1 upon XC. So from here we can find out the impedance. This is, let us, equation number 2. Now we know that 1 by Z is equal to admittance, so we'll write it as Y, which is equal to G, because 1 by R is G. minus J, and then we have 1 by XL is equal to BL, right? And then 1 by XC is equal to BC. So this is your equation number 3, right? So as far as the phasor diagram is concerned, so depending upon the 3 cases, so case 1, if BL minus BC is greater than 0, that is positive. So BL is greater than BC, right? So case 2 is BL minus BC is less than 0, that is negative, or BL is less than BC, right? So case 3 is BL minus BC is equal to 0, or BL is equal to BC. So this is the special case, right? So the phasor diagram can be drawn in all the cases. The first is BL minus BC is positive. So we have, first of all, we'll take the current phasor, which is IR, and then we will take the voltage phasor, which is, let us say, V, and then again we will take the, now if you see here, in this particular circuit, in resistance, the if we draw the phasor diagram here, so the voltage V and the current IR are in same phase. Voltage V is leading the current IL by 90 degrees, and voltage V and and the current, the current is leading the voltage V by 90 degrees, right? So we can apply the same concept here also, right? Now the current across inductor would be lagging, and the, so let us draw it. So first of all, we have the IC, which is leading the V by 90 degree, and then we have IL, which is lagging the voltage by 90 degree. Now the question is that where will be the resultant phasor lie? The resultant current will depend upon whether the given RLC circuit is inductive or capacitive, right? So this we can understand from the concept which we understood previously. Like if our circuit is capacitive or an inductive circuit, we can see that the phasor, the resultant phasor, is existing in the 4th quadrant basically. So this is the 4th quadrant. So the phi is negative here. And if we talk about the capacitive circuit, if the circuit behaves as a capacitive circuit, the resultant current is existing in the 1st quadrant because phi is positive here. So the same concept can be applied here. So case 1, if the circuit is inductive, then, and the case 2 would be if the circuit is capacitive, right? Now in this case we have the IR, and we have V, and we know that the net current is, because the circuit is behaving as the inductive circuit, so it is IL minus IC is lying here, and the resultant current is this one. This is I, and I is, this is the angle phi here, right? So this is what is the current. So this leads to the current triangle. So we can draw the current triangle also. So the current triangle would be your IR, and the net current IL minus IC, and then you have the net current I. So from here we have I is equal to IR plus IL minus IC, right? So this is the phasor sum. Okay. So as far as the admittance triangle is concerned, so admittance triangle can be done. Now this is the current triangle. This is the current triangle. Now admittance triangle can be obtained by dividing this with V. So if we divide it with V here all around, so we will get the admittance. So IR by V is equal to G. IL minus IC by V is nothing but BL minus BC. And this is nothing but the admittance. Fine. So Y is equal to your G minus J BL minus BC. Right. So the magnitude of Y is equal to under root G square plus BL minus BC square. And the phase angle is your tan inverse. So this is BC minus BL by G. This is the phase angle. Now let us come to the capacitive part. If the circuit behaves as a pure capacitive, not pure capacitive, a capacitive circuit. Okay. So in this also we have the current phasor IR. Then we have the voltage phasor V, and the resultant current would be in the positive. So it is, IL minus IC is positive here, right? And the resultant is your current IE. This is fine. So from here you can draw the current triangle also. So the current triangle is, this is your IR, and then you have IL minus IC, and then you have this one I, and the angle phi is there. So this is the current triangle, right? Okay, so from here we can get the admittance triangle also, but the equation of I is equal to IR plus IL minus IC. So in both the cases we have the same equation kind of. Now the admittance triangle is obtained by dividing this with V all around. So we have the IR by V is G, and this is BL minus BC, which is positive in this case now. And this is angle phi, and this is the admittance. So admittance in this case is G plus J BL minus BC. Right. So we have the magnitude also. The magnitude is under root G square plus BL minus BC square. And the phase difference is tan inverse, you have BL minus BC divided by G. The phase difference is always obtained by using this formula, tan inverse of the imaginary part of the complex quantity to the real part, right? So in this lecture, we have understood in detail about the RLC circuit. We have understood about how to find out the total current in the parallel circuits, whether it is RL circuit or it is RC circuit or it is RLC circuit. And we have also seen the phasor diagram of these three types of circuits. In our electrical systems, the parallel circuits are more preferred as compared to series circuits because our electrical components or devices share the same voltage rating. So to give them the same voltage, we need to connect them to each other in parallel across the voltage source. Also, instead of using the impedance, we use admittance. Instead of using resistance, we use conductance, and instead of using reactance, we use susceptance in parallel AC circuits. Now, this was all about today's class. Thank you so much.